Hello everyone, welcome to my presentation with the title Towards Robust Indoor Visual SLAM and Dense Reconstruction for Mobile Robots. My name is Wei Zhang. I'm a PhD student at the Institute for Photogrammetry, the University of Stuttgart, and Huawei Research Center in Munich, Germany. The motivation behind this work is that mobile robots are being increasingly deployed in various scenarios, such as autonomous operations in manufacturing and services. Visual SLAM is an essential part to provide robots position and a map for collision-free navigation. Besides, the dense reconstruction is important for environment modeling, such as for construction sites. However, we observed several challenges for visual SLAM systems. First one is the failed camera pose checking due to low texture or camera view blocking, as can be seen when robot approaching and passing the white wall. The system failed to check, resulting in unsmooth trajectory. The second challenge is the global inconsistency due to pose drift error without successful loop closures and leading to inconsistent map, as can be seen on the right figure. The third challenge is the inaccurate depth observations, especially at far ranges, as can be seen in the right video. Here is our system overview. As input to our system are the RGBD image streams and view encoder measurements. The goal is to produce accurate camera trajectory estimate and a globally consistent and complete map. The first submodule of our system is the SLAM front end. The front end receives the inputs and constructs a local bundle adjustment, which consists of three different types of constraints within a sliding window. The first constraint is the reprojection constraint. We use dense optical floor prediction as targets, while current reprojection at the time of optimization can be computed with the current depth estimate and the current pose estimate. The second constraint is the view odometry constraint, with the integrated view encoder measurements between consecutive keyframes. The third one is the depth prior constraint. Inverse depth distance as error turn to be in favor of closer depth observations, which are more accurate. The second submodule of our system is the dense reconstruction module. We construct truncated sign distance field using depth map inputs and estimated camera poses from SLAM front end. Submaps are also created regularly to keep pose drift error minimum within a submap, which are prepared for the subsequent submap registration. The third submodule of our system is the SLAM backend. It performs global bundle adjustment, which includes all keyframes with 4 different types of constraints. While the first 3 constraints are the same as the front end, the additional constraint is the submap registration constraint. It's computed for each pair of submaps with overlaps. The error terms are computed by projecting isosurface points of the one map to the TSDF of the other map, and minimizing the sum of lookup TSDF distances. Before the final combined map is constructed, a depth map refinement step is performed. Refined depth maps are the combination of, on the one hand, optimized depth maps for multi-views in global bundle adjustment. On the other hand, smoothed depth maps using bilateral filter. Depending on the confidence, if the confidence are high for the optimized depth maps, or the smoothed depths are missing, the optimized depths are taken. Otherwise, the smoothed depth values are used for the refinement. Here are 2 representative results for depth map refinement. As can be seen, the input sensor depths are noisy, especially at object border and far measurements. Besides, there are also missing values. These missing values can be reasonably estimated by optimization. As for the measurements at object borders, this can be improved by both smoothing and optimization. However, for the thin objects, we notice that smooth depth has a better result. As for our final refined depth, it benefits from the strengths of both optimization and smoothing. Now I would like to present our experimental results. We collect our own dataset using Turtleboard platform and RealSense camera. 6 room-size sequences were corrected with the post-ground tools provided by the motion capture system. The used metric is the absolute trajectory error. As the table below shows, our extension with the VO encoders and submap registration reduce the mean errors. In comparison with the state-of-the-art methods, our accuracy is also favorable. Further quantitative experiments are conducted on synthesized data. We synthesized 153 sequences from HM3D dataset to validate the effectiveness of our method on larger multi-room scenes. As the table left shows, our extension on the baseline with the VO encoder and submap registration can reduce the overall error, especially for the mean error and maximum error. The figure below shows the cumulative error distributions. The upper left means more robust. As can be seen here, our combined solution with both VO encoder and submap registration has achieved the best robustness. Here we show a representative sequence from the synthesized data. In this sequence, submap registration has played an important role to mitigate drift error after long movement. The figure on the left and the right side is the output without and with submap registration. As can be seen, the loop can be closed successfully with the submap registration, and pause error is minimized. This difference is also reflected in the map. As can be seen, the inconsistency can be observed in the left. Here is the qualitative result on OpenRoll's dataset to especially showcase the challenge by low texture. As mentioned in our motivation, the vision-only system can fail to check the camera pose in case of low texture. While using the VO encoder inputs, it can help to keep the camera pose checking in this challenging scenario, and smoothing trajectory can be estimated as shown in the video. Along with trajectory, the final reconstructed 3D map is evaluated quantitatively. For this purpose, we have collected a multi-room sequence with a reference map by a high-precision laser scanner. The evaluation is based on 2 matrices. On the one hand, the accuracy is computed by the distance from the reconstruction to the reference map, as shown in the figure left. On the other hand, from the perspective of completeness, this is computed by the distance from the reference to the reconstructed map, as shown in the figure right. In the end, we have an accuracy of 7.8 cm and a completeness of 6 cm. In conclusion, we have proposed a robust indoor visual SLAM and dense reconstruction framework. This framework has addressed the following 3 main challenges, which are low texture, long-term inconsistency, and noisy depth measurements. In the future, we would like to enhance further the robustness with IMU measurements. Furthermore, we would like to increase the depth accuracy more by incorporating a depth refinement network. Thank you for your attention.